Good evening, my friends. Myself Kanishk Patil, and today I am going to present a PPT on INYPT's problem number 14. So I will share the screen. So welcome to INYPT's problem number 14, the soap spiral. Okay. So the index in this PPT is understanding the statement of the problem, basic parameters, observation of the phenomenon, explanation of the phenomenon, problem faced during the experiment. So first, before beginning the experiment, we will first see, we will first understand the statement of the problem. So the statement states that lower a compressed slinky into a soap solution, pull it out and straighten it. A soap film is formed between the turns of the slinky. If you break the integrity of the film, the front of the film will begin to move. So here you have observed that I have underlined the word soap solution and integrity of the film. So let's see what these terms mean and how their importance affects our experiment. So first, let's see the soap solution. So a soap solution is basically a solution which contains soap. So it is considered as a colloidal solution since it contains a dispersion medium and a dispersed phase. So you may be wondering what is a colloidal solution. So a colloidal solution, it is like a heterogeneous mixture made up of two phases, namely the dispersed phase and the dispersion medium. For example, soap solutions, milk, fog, and etc. And also, the colloidal solutions show Tyndall effect. It means once we pass the light from these solutions, it reflects or the path of the light from these sources, from these solutions become visible to us. Then second, the integrity of the film. Here it means the nature of the soap film, which means how undivided is the soap film. In this slide, we can see how the film maintains its integrity. Here we can see there is a ring and we have dipped the ring in the soap solution and we can observe that how the soap film has maintained its integrity in this on this shape. So the basic parameters before starting the experiment. So every experiment needs some basic conditions which are need to be met to start the experiment. So these parameters for my experiments are quality of the soap solution, stability of the soap film, and the third and the most important, the atmosphere should be a bit humid. It should be done in cool and shady places. And most important, slow motion cameras. So observation of the experiment. So step one was the dip the compressed slinky into the soap film. Step two was then expand the slinky, and we will observe that the soap film is formed around the curves of the slinky. And step three, once we break the integrity of the film will start moving in the upward direction. So this was the observation. Now let's explain or let's see how the phenomenon actually works. So before starting, let's see how a soap film forms. A soap film is formed between a water layer which is sandwiched by the two layers of the soap molecules. Here you can see there are in this image you can see like there are some red molecules and a tail over there. So and this blue region represents the water. So the red circles represent the hydrophilic head. Hydrophilic means water loving head. That's why it's the direction of the head is pointed towards in the water direction. That's why the sandwiched layer we can see in the image. And the zigzag tails here represent the hydrophobic tail, which means the water scaring or they don't like water. So they are faced in the opposite direction of the water. Stability of the soap film. So in our experiment, the stability of the soap film is very important because if once we dip the slinky into the solution and expand it, sometimes the soap film may not form. So we have to see that the soap film must form to continue with our experiment. So the force between the air column inside the slinky and outside the slinky should be equal, which will make sure that the soap film's integrity is maintained. Actually, the presence of soap, which is composed at a molecular scale of surfactants, is necessary to stabilize the film. Most of the time, surfactants are amphiphilic. Amphiphilic means that they are molecules with both a hydrophobic and a hydrophilic part. Like we saw in the previous slide, here is an image of the soap film, and this is the surfactant, which is amphiphilic in nature. It means it has both a hydrophilic head and a hydrophobic tail. So, what is a surfactant? Surfactants are chemical compounds that decrease the surface tension or the interfacial tension between two liquids, a liquid and a gas, or a liquid and a solid, for example, detergents. So, you imagine there's here, let's get back to the image. So, imagine this is that water layer formed around the soap film. This is medium 1 and this is medium 2. The medium 2 exerts a surface tension in this direction, in the bottom direction, and the surface tension exerted by the upward region is exerted in the upward direction. So this both regions tend to pull this water layer towards themselves. But here the role of surfactants is to decrease the surface tension or the interfacial tension between these two mediums, this medium 1 and medium 2. So let's see the next slide. Then here, what is the role of the surfactant? As I have explained, surfactants restabilize films because they create a repulsion between both surfaces of the film, preventing it from bursting. And surfactants make the thickness of the film uniform throughout due to the Marangoni effect. So you may be wondering, what is the Marangoni effect? So it is the mass transfer along an interface between the two phases due to a gradient of the surface tension. So let's see a practical example of it. You must have done it. So here you can see the practical example of Marangoni effect. So here I have a bowl of water and a pepper sprinkled on above the water. This pepper is floating on the surface of the water, and I have dipped my finger into into a soap solution before, and then I dipped it in this bowl of water. So as I dip the water, the soap solution gets dispersed in this water in this bowl. So because of the difference in the surface tension, the peppers go away from the soap solution which I dipped. And because of this phenomenon, it is known as Marangoni effect. Here, a liquid with high surface tension pulls more the surrounding liquid than one with a low surface tension. Minimal surfaces property. This property is very important in our day-to-day lives. For example, in mathematics, when we need to calculate minimal surfaces property of or minimal surfaces of any surface, we need to use heavy computers, supercomputers, which will calculate the area of each and every line joining each in every area joining the two most closest parts on the outer surfaces of the shape. So, but due to the soap film, this process becomes much more easier. So, minimal surface is the surface of smallest area of all the surfaces bounded by a closed curve in space. A minimal surface is a surface satisfying the zero mean curvature property. In the case of soap films, the potential energy resulted from the intermolecular force between the molecules of soap and water. Consequently, this energy is directly proportional to the surface area of the soap films, assuming that the thickness of the soap film is uniform, which we saw in the previous slides, which is done by the Marangoni effect. And as a result, the soap films achieve minimal area. So here in this image, you can see the minimal surface area property. We have dipped a cube in the soap film, and this for to claim or like to get this result, we need to by using mathematics, we need to use very much supercomputers to obtain this result. But with a soap film, it is done in seconds. So once we are in our experiment, we are bursting the soap film with a pen. So let's see how bursting of a soap film takes place. A soap film can't always remain stable, and in our experiment, we broke the integrity of the soap film. As the whole, it opens very rapidly. Surface tension indeed leads to surface minimization and thus to film disappearance. The whole aperture is not instantaneously and is slowed by the liquid inertia. As in my experiment video, we saw that the soap film moved in the upward direction like a roller coaster when the integrity was broke with a pen. So you may be wondering, the bursting of the soap film takes place and the soap film is moved in the upward direction. So the soap film will move in the upward direction with a certain velocity, and that velocity is represented by this equation. So here, gamma represents liquid surface tension. Here, H means the film thickness, and rho means liquid density. So we have also calculated the velocity of the soap film. So in my experiment, gamma, which means liquid surface tension, was 30 millinewtons per meter. And here, and the rho or the liquid density was 1100 kg per meter cube, and the film thickness was 30 nanometers. So after calculating, I got a very interesting speed, which was very fast, which was 42.426 meter per second, or also 151.2 kilometer per hour, which is very fast, and that's why we can't see with our naked eyes. So we need to use slow motion cameras to detect this phenomenon because it occurs at a very great speed. So here, this slide contains the explanation of the phenomenon in a nutshell. As we break the integrity of the soap film ruptures apart and a hole in the soap film occurs. As after breaking, as after breaking the integrity of the soap film wishes to minimize its area by following the property of the minimal surfaces which we saw in the previous slide. So as it wants to minimize its surface, it moves upwards and upwards to the beginning of this slinky. And as it moves in the beginning of the slinky, that motion occurs in the upward direction along the slinky. And this motion has also occurred like the surface tension pulls it pulls it in the direction upwards, in the direction of the upward direction, to minimize the surface area, like to follow its property. So many every experiment faces many problems. During every experiment faces many problems. So here the problem we faced was the stability of the soap film. So first we were trying to make a film stable, but then later we made a research and found out that by diluting some parts of soap and dishwashing liquid, or Dettol, and in water, we can make a good soap film. Capturing the phenomenon. As I stated before, capturing the phenomenon was like a very was like a very difficult task because it occurred at very huge and great speeds. That's why we can't record the phenomenon with our basic cameras. So I installed slow motion cameras to capture the phenomenon. So this was the problem faced during the experiments. So thank you. I think you liked it. So please.